All right, here we go. Compound probability is when we have events that happen one after the other. Because these things happen in succession, it's common for us to call those successive events. So when we say successive events, we're talking about one thing that happens, and then after that, another thing happens. It's important to keep in mind that we only have a success when both things happen. So in order for us to have a success as far as calculating probability is concerned, the first thing has to happen and the second thing has to happen. I like the opportunity to use the word "and" here because it leans back into set theory from Math 122, where the word "and" the word "both," that was the overlap of our Venn diagram. That was the intersection of those things. It's kind of nice that it stays consistent no matter what topic we're covering, that all those words and all those sort of concepts don't really change. Okay. When we want to calculate compound probability, the way that we do that is very reminiscent of what we saw when we did the fundamental principle of counting. We're going to find the probability of each event and then multiply those probabilities together. So just like we did with the fundamental principle of counting when we said find a number of choices for each stage and then multiply those together, now when we're going to have successive events, one after the other, we're going to find the probability of the first event, find the probability of the second event, and then multiply those together to get our compound probability. Let me know if you have any questions on that before we take a look at one. All right. A jar contains 5 green, 3 white, and 4 red marbles. A marble is selected, then replaced, and another marble is selected. What's the probability that the first marble is green and the second marble is red? We're going to talk about this situation a little bit before we answer the question. So we have this jar and we can see the marbles that are inside it. And a marble is selected, then replaced. That's a really important word for us because that means we're going to take this marble out, write down what it was, put it back in, mix them up again, and then select another marble. Here we are replacing that first marble. That won't happen all the time, and it changes things a little bit when we don't replace. But in this particular case, we are going to replace it. And so let's see here. We're asked to find the probability that the first one is green and the second one is red. So we want green followed by red. You're going to hear me say single specific outcome during class today. And when I say a single specific outcome, what I'm talking about when I say that is something like this: green followed by red. That's it. That's a single specific outcome. That's the only one we care about. There's a lot of things that could happen here when I pull these marbles out of the jar, but the only one I'm looking for is green followed by red. It's just that is the outcome that I'm looking for here. Single specific outcome will make more sense when we get later into class and we're talking about tree diagrams, but I just want you to kind of be familiar with those words so that when I say them later on, you know what they mean. Okay, so our job here then is to find the probability of the first event. So that's getting a green on the first draw. Probability is successes over outcomes. Remember, no matter what kind of probability question we're working on, we're going to keep the most important thing about probability in mind. It's successes over outcomes. All right. So let's see here. I have 5, 6, 7, 8, and 4. I have 12 total marbles. So I'll just ask you, what's the probability that I get a green marble on that first draw? Perfect, Jennifer. It's exactly right. It's 5 out of 12 is the probability I get a green marble on that first draw. Okay, now what I'm going to do is I'm going to put that marble back in the jar, mix them all up. What's the probability I get a red marble on the second draw? And again, any of you can just type it in for me. The probability of a red marble on that second draw. Perfect, Jennifer. And where that's coming from is I have 12 outcomes, so I know my denominator is going to be 12. I have 4 red marbles, so my successes are 4. And so I have 4 successes, 12 outcomes, so the probability of getting a red is 4 out of 12. And so the probability of getting green followed by red, we'll just multiply those together. We have to remember multiplying fractions. And let's see, to multiply fractions, we just multiply numerators. 5 times 4 is 20. Multiply denominators. 12 times 12 is 144. And so the probability of getting green followed by red is 20 out of 144. Remember, all probabilities are between 0 and 1. That one certainly is. You could reduce it to, I guess, what would it be? 10 out of 72. Those are both even numbers, so 5 out of 36 if you wanted to. But you don't have to. You could just leave it as 20 out of 144. Are there any questions on that before I have you try one? Okay, here goes. Same jar, 5 green, 3 white, and 4 red marbles. A marble is selected, then replaced. What's the probability the first marble is red and the second marble is white? I'll set up a poll for this and give you a chance to try it. So the setup here is just like the last one. It's just now we're looking for the probability of getting red followed by white. And just at its surface, this is sort of our most basic, straightforward compound probability type of question. So this is a great place for us to start because it's just, this is sort of the backbone of it. We're going to look at more complicated scenarios, but the idea that we have one thing followed by another thing, that's what's going on here. Go another 20 seconds on this, and then we'll talk about it. All right, let's see how this one went. Unanimous. Fantastic. That's always good news. Okay, very good. If you're unsure of anything in here, please don't hesitate to ask about it. But the idea that it was a unanimous response is very encouraging. That's terrific. All right, so let's go ahead and take a look at this one then. We need the probability that we get red followed by white. And so we're going to find the probability that the first one is red, and that's going to be 4 out of 12. And then the probability that the second one is white, which is going to be, let's see, that's going to be 3 out of 12. Sorry about those circles. It's the new, there we go. Now we should be a little better. 3 out of 12. And so we're going to multiply those together. 4 times 3 in the numerator is 12. 12 times 12 in the denominator is 144. And so our probability of red followed by white is 12 out of 144. Let me know if you have any questions about what happened there before I have you try another one that's just a tiny bit different. Okay. A jar contains 5 green, 3 white, and 4 red marbles. Same jar. One marble is selected and another marble is selected without replacement. And the key here, what makes this different from the others, is without replacement. When you see that, what it means is I pick the first marble out, I leave it out, and then I go pick the second one. I'm going to set up a poll for this one for what is the probability the first marble's red and the second marble is white. So the difference between this one and the last one is that we're doing this one without replacement. Those are important words. So we want to make sure we're confident with what those words mean and how they impact the way we approach the problem solving. And so while the last question was probably the most basic compound probability question we would see, this is just one step up from there, as it's very much the same, except we're doing this without replacement. And we have to know what that means and know how to implement it. Go another 20 seconds on this one, and then we'll talk through it. Now let's see how we did here. All right, unanimous again. Very good. I do have to say that as a class, you've been a really strong group all semester long, and that just seems to keep being consistent. So that's excellent. Great job on this one. Let's take a look at it together just to make sure that we're all comfortable. What we're going to have here is we're going to draw these out, but this time it's going to be without replacement. We want the probability of red followed by white, and probability of red on the first one, that's 4 out of 12. And here's where the change comes in. The probability of getting white on the second draw, the key is we started with 4 red, but we took 1 red out. So at this point now, we only have 3 red left in there, which means we only have a total of 11 marbles in there. Now, all 3 white ones are still there, so the probability of getting white is 3 out of 11. We'll multiply those together and wind up with 12 out of 132. And again, that could reduce, but you don't have to reduce it. Any questions on those marble from a jar type of questions that are sort of our introduction to successive events? All right, fantastic. This is one that may not read as a successive events question right away, but once you're familiar with it, you'll see it that way. Catherine has applied for a job with Globo Corp. There's a 48% chance she will get an interview. If she gets an interview, there's a 30% chance she will get the job. What's the probability that she will get the job? And this time we're going to express our answer as a decimal. I want to make sure you're comfortable writing probabilities as fractions or as decimals, so you're going to see both ways. And here the question is really just what's the probability she will get the job? Well, what we have to do to see this in the correct light, to see this as a problem that involves successive events, is first she has to get an interview, and then after that, she has to get the job. So the compound probability we're after here, the successive events we're after here, is the probability that she gets an interview followed by her getting the job. So those are the probabilities we need to multiply together. Probability of an interview multiplied by probability of a job. We kind of get comfortable with the idea that percents are always going to be fractions, but they can be decimals too. And then in this case, we can see there's a 48% chance she will get the interview. So here, we're not looking to write this as successes over outcomes. That's already been done for us. It's been written as a percent. We just need to turn that percent into a decimal, 0.48, and then that's what we're going to use as the probability she gets an interview. So really, it was just given to us. We didn't have to find successes and outcomes here. It's just right there in the problem. 48% chance means the probability is 0.48 that she'll get the interview. And then since there's a 30% chance that she's going to get the job after getting an interview, then that's going to be 0.30 as a decimal. So that'll be 0.30. And just like with other successive events questions, Find the probability of the first event, find the probability of the second event, multiply those together. And so here, what we're going to have is 0.48 times 0.30. And I get 0.144. All probabilities are between 0 and 1, so this answer is reasonable. It doesn't guarantee it's correct, but I didn't get something like 22, which I would know is wrong. And then I was told in this one to round to the nearest hundredth. So we'll find the hundredths place with one space to the right. That's 4 lower. So we'll round this down to 0.14. And so that's the probability that Catherine's going to get the interview, and then after that, get this job. Let me know if you have questions on that one. It's much easier than it first appears. And sometimes it can be so simple that it actually can throw students. Sometimes I don't want that to happen to you. Okay. Here's one that is successive events. It involves fractions, kind of like our drawing marbles from a jar, but this is a real world type situation. So I just want to make sure we're comfortable with it. There's a 2/7 chance that Natalie will go to the grocery store today. When she goes, 3/5 of the time she spends over $50. So what's the probability she spends over $50 at the grocery store today? So in this one, what we're looking for is very similar to the last one with Catherine getting the job. Is first she has to go to the grocery store, and then if she goes, she has to spend over 50. Okay, those are our successive events. So we need the probability that she goes to the grocery store and then spends over 50. Well, probability she goes to the grocery store is 2/7. The probability she spends over 50 is 3/5, and we'll multiply those together to get the compound probability that she's going to spend over 50 at the grocery store today. Numerator, 2 times 3 is 6. Denominator, 7 times 5 is 35. And so the probability that she's going to spend over 50 at the grocery store today is 6 out of 35. In the last problem, we saw a probability as a decimal. Sometimes you're going to work problems, maybe a problem like this one, and it might say at the end, express your answer as a decimal, just to make sure you're all comfortable with that. You can work the problem entirely in fractions. And then once you get to the end, if you need to write it as a decimal, this 6 over 35 really just means 6 divided by 35. And so if we do 6 divided by 35, we get, I'm going to round to the nearest hundredth, 0.17. And so I just want you to recognize that, take a quick look and make sure you're formatting your answer the way you've been asked for it, whether it's as a fraction that you don't have to reduce or as a decimal. If you're asked for a decimal and you're here, there's just one more step to do, just divide, and then you'll have the decimal version of that percent, or excuse me, of that probability. Any questions on that one? Okay, very good. Now we'll talk about tree diagrams. Tree diagrams are going to be great for us when our situations are a little more complicated or when we are not after a single specific outcome. If you think about every problem we've done so far, it was green followed by red, red followed by white. She gets the interview, she gets the job. She goes to the store, she spends over 50. There was a single specific outcome. Tree diagrams come in to be really useful and necessary when we are not after a single specific outcome. You might be thinking, well, what would that even look like? And that's a really fair question. And I'll just ask you to hang in there with me for a little while because we'll get to see some of those. And they're very obvious. Okay. The first thing I want to do with you, though, is just show you how we make a tree diagram, what one looks like, and clear up any misconceptions that are common with tree diagrams. So we're going to go ahead and make one. And the situation we're going to use is going to be extremely simple. You know, I did say tree diagrams are great when the situation's complex, but I want to start out with a very simple situation so that, you know, we have a very comfortable way to get our feet on the ground. We'll make them more challenging later on, but for right now, let's start out very basic. Parents are going to have 2 children. Create the tree diagram for this situation. So here's how a tree diagram works. We're starting, they don't have any children, and they're going to have that first child, and it's either going to be a boy or a girl. And so we draw those lines because those are the paths that this could possibly take, a boy or a girl. And we also put the probabilities right there on our tree diagram. The probability of having a boy is 1 out of 2. Probability of having a girl is 1 out of 2. And so that's our first potential, that's our first child and the possibilities that could happen. They're going to have another child. And then if we're up here, that means the first child was a boy, and then they're going to have another child, and that second child is either going to be a boy or a girl. And then those probabilities are also going to be 1/2 for the boy, 1/2 for the girl. But one thing we haven't considered yet is what happens if the first child is a girl? We haven't done that yet. We've only looked at what if the first child is a boy. So we also need to put possibilities down there. And the first child's a girl, and then the next child could either be a boy or a girl. And we'll go ahead and put those probabilities on there too. All right, I'm going to pause here for just a second because it's not uncommon. It happens quite a bit for students who've never worked with tree diagrams before, and that could be all of you, to look at this and say, wait a minute, you said they were going to have 2 children, and I'm looking down here and I'm seeing 1, 2, 3 children. But you said they were only having 2, so why are there 3? It's an excellent question, and here's why. You see those 3 different things. The first child is over here in this column right here. That's child number 1. And then this second column here, that's all just child number 2. Because what's going on in this one is this only happens if the first child is a boy. This only happens if the first child is a girl. So what we're doing is we're making sure that we account for every possible condition. I'm going to have to draw those back in, but we're making sure that we're accounting for every possible everything that could possibly happen. And so that's how this column here just represents 1 child being born. It's because it's dependent on whether the first child was a boy or a girl, which path you take. And that's kind of how we're going to look at these. We're going to follow paths. And here's what I mean by that. The first child could be a boy, and then the second child, a boy. And if we follow that path, they had boy followed by boy. And if we want the probability of that happening, we are going to multiply the probabilities that we encounter along that path. So our successive events, the first one was a boy and the second one was a boy. So we are going to multiply these 2 probabilities together. And we're going to do 1/2 times 1/2. And the probability of having boy followed by boy is 1/4. Please let me know if you have any questions about anything that I'm saying, because understanding how a tree diagram is created and then how it works can be challenging. Ideally, you're like, makes perfect sense to me, and that's awesome. But if that's not the case, please don't hesitate to ask your questions. There's extreme value in being able to have a live class like this, and that extreme value comes in where if there's something you see that you're unsure of, you can ask about it right now and get an answer right now. Okay, we're going to do this along every path. So we're going to have boy followed by girl. And that's going to be 1/2 multiplied by 1/2. The probability is 1/4. Moving further down a little bit, we'll have the first child's a girl followed by a boy. So here we have girl followed by boy. And those probabilities are 1/2 times 1/2 or 1/4. And then finally, the last one we have is girl followed by girl. And those probabilities, 1/2 times 1/2, that's also going to be 1/4. When I say this is a very basic and very simple situation, that's kind of what I'm talking about is what we end up with over here isn't that dramatic or interesting because all the probabilities are the same, but that's perfect for us getting our feet wet. What we've done now over here on the right of this, what we've done over here is we have created our sample space. Now what we can do, no matter what kind of question we're asked about this family that's having 2 children, is we can answer questions using this sample space that we just created. Let me show you what I mean by that. Parents are going to have 2 children. Find the following probabilities. The first one we're asked for is what's the probability that they have 2 boys? So this is the probability of having boy followed by boy. If you're thinking, that looks like a single specific outcome to me, boy followed by boy, do I need a tree diagram for that one? Honestly, you don't. You could just do this one as 1/2 times 1/2 is 1/4 and you're done, because it's a single specific outcome. But we went to the trouble of making the tree diagram. We went to the trouble of making the sample space. Let's go see what our answer is going to be here. So we'll go back and we'll say, all right, boy followed by boy, that has a probability of 1/4. So my answer here is just 1/4. All right, now we get to the ones that are not single specific outcomes. This is where tree diagrams kind of ramp up a little bit. So please tell me if and when you have questions. So the first one we're going to look at here is find the probability of having exactly 1 boy. The reason this isn't a single specific outcome is because there's more than one way for this family to have exactly 1 boy. Go look at our sample space. Exactly 1 boy. So exactly 1. That means no more, no less. Exactly 1 boy. So here it's boy followed by boy. That's 2 boys. So that's no good. That's not going to be a success in this case. Boy followed by girl. Yeah, that's exactly 1 boy. So that's going to be a success. Girl followed by boy. Yes, that's exactly 1 boy, no more, no less. And girl followed by girl. No, they don't have any boys down there. So that one's no good. So what we found out here is there's more than one way to have a success. This is key, and this is a really important point. They could have a success this way or this way. Going back to set theory in Math 122, or meant union, meant join together. When we looked at a deck of cards and we could call a success a 7 or a heart, we needed to add the 7s and the hearts. We don't want to count anything twice, but we're going to add those together, and that's what we are going to do here. Because there's more than one way to have a success. We can have a success this way or this way. We are going to add those probabilities together. And so what we're going to have then is the probability of getting exactly 1 boy is 1/4 plus 1/4. We haven't added fractions yet, but just a reminder, when we add fractions, we add the numerators. 1 plus 1 is 2. Denominator stays the same. And so the probability of having exactly 1 boy is 2 out of 4. And so that's going to be our result here. The probability of exactly 1 boy is 2 out of 4. I want to go back and talk for just a second. Sometimes students will get a little confused about, okay, well, so you're telling me that sometimes we need to multiply and sometimes we need to add. That's exactly right. And the times that we need to multiply are only when we're walking along, oops, sorry about that one. When we're walking along these paths. When I walk along the path, one event followed by another, that's when we multiply. Once we've created our sample space, we're done multiplying. That's it. At this point, if there's more than one way to have a success, we're going to have to add. Please let me know if you have any questions on that, because that's where this can get a little complicated. All right. The last one here said, what is the probability of getting at least 1 boy? At least one boy. So that's at least one boy. All right, let's see. So boy followed by boy. Yep, there's at least one boy in there. Boy followed by girl. Yep, there's at least one boy. Girl followed by boy. Yep, there's at least one boy. Girl followed by girl. No, there's not one boy down there. So I could get at least one boy this way, or this way, or this way. So I need to add those probabilities together. And I'm going to have 1/4 plus 1/4 plus 1/4 is 3/4. The probability of getting at least one boy is 3/4. All of the probabilities in that setup were very simple and straightforward. What's going to change for us as we look at future examples is the probabilities won't be so simple. The concept of making the tree diagram, multiplying to find our sample space, and then if there's more than one way to have a success, we add them together is going to stay the same. It's just that the probabilities will be a little more complicated. Are there any questions on anything we did in creating the tree diagram, creating the sample space, and finding the answers to those 3 probability questions? Outstanding. All right, let's keep going. A jar contains 6 blue and 2 yellow marbles. 2 marbles will be drawn, one after the other, without replacement. First thing we're going to do is create the tree diagram for this situation. I'm going to make it, but I'm going to have you help me along the way. So the first thing that can happen here is I pull out a marble, and there are 6 blue and 2 yellow. So I'm either going to get a blue marble or a yellow marble. And the probability of getting a blue one is going to be 6 out of 8. If anything that I do raises questions, make sure you ask them. But the probability of getting a blue one is 6 out of 8. And the probability of getting a yellow is 2 out of 8. Okay, now I need to draw another marble. And it's really important to note that this is being done without replacement. So I'm doing this without replacement. All right, I could get a blue or a yellow. And then even if the first one's yellow, for the second one, I could get blue or yellow. This is where your part comes in. I see we lost a couple. That's unfortunate, but that's okay. So, all right. What we're going to ask for first is the probability that's going to go right here. Keeping in mind, I started with 6 blue and 2 yellow. And if I've followed this path, that means the first marble I've picked is a blue one, and I'm doing this without replacement. So what's my probability going to be up here? And if you don't know, that's okay. If you do know, you can go ahead and share it with us. Once you see this one, I think the rest of them will kind of fall into place for you. And if you say something and it's wrong, it's okay. A couple of 5 out of 7s. Very good, Nadine Summer. And hopefully Brisant. Yes, very good. I started out with 8 marbles. I took one out and it was blue. So now I've taken one out. So I only have 7 marbles left. I started with 6 blue. I took out a blue one. That means one of my blue ones is gone. So instead of 6, now I have 5. Okay. And then the probability here of getting a yellow on that draw, what would that be? Because I think building this tree diagram and then getting to our sample space is the challenging part of this. I think you'll be good at answering the questions. Yes, some are 2 out of 7. I started with 8. I bought a blue one. That means I have 7 left in my jar. And I started out with 2 yellows. The one I took out was blue. So both yellows are still in there. So that's 2 out of 7. All right, now on the bottom half of this, I'll do them and you tell me if it doesn't make sense to you. I started with 8. I bought a yellow one and I left it out. So what that means is that I have 7 marbles left in the jar. I started with 6 blue. I bought a yellow, so I still have 6 blue in there. So the probability of getting a blue there is 6 out of 7. I don't like the way that shaped up, so let me redraw that. That'll be 6 out of 7. I started out with 8 marbles in the jar. I bought one, so now I only have 7 left. I started with 2 yellows. I bought a yellow. So what that means is I only have 1 yellow left in the jar, so the probability of getting a yellow is 1 out of 7. Before I do anything else, I want to make sure you're all comfortable with what's in that tree diagram, with all the probabilities that are on there and the way that it looks with the blues and the yellows. All right. Now we've got our tree diagram drawn because we are drawing 1 marble out over here, another marble out over here. Those are our 2 that we're going to get. So we're all done. Now what we need to do next is figure out, okay, what are the probabilities of each of these events? So what does my sample space look like? So if I go blue followed by blue, the probability is going to be 6/8 multiplied by 5/7. And multiply numerator, 6 times 5 is 30. Multiply denominators, 8 times 7. Now, that's one that I always have trouble memorizing. It's okay to use a calculator just to make sure. 56. All right. So the probability of getting blue followed by blue is 30 out of 56. This is already much different than the last question as far as probabilities go. We're not going to have 1/4 right down the line. The reason for that is because the number of blues and yellows isn't even, so our probabilities are going to be different as we go through this. Up next, we're going to have blue followed by yellow. Okay, so blue followed by yellow, and I multiply those. 6 times 2 is 12. 8 times 7 is 56. Kind of nice. Our denominator is going to stay 56 all the way throughout. We're going to have 56 outcomes here. That makes sense from the fundamental principle of counting. I started out with 8 marbles. After I took one out and left it out, I had 7 marbles. How many choices for the first space? How many choices for the second space? Multiply those together. We should see 56 outcomes here, and that's exactly what we're seeing in every one of these probabilities. Up next, we've got yellow followed by blue. So we're going to multiply the probabilities along that path. 2/8 times 6/7. And 2 times 6 in the numerator is 12. 8 times 7 is 56. And then finally, we'll have yellow followed by yellow. 2 times 1 is 2. 8 times 7 is 56. What we've done now at this point is we've created our sample space with their probabilities. That's everything that could possibly happen and all the probabilities that go with them for this situation. Before we start answering any questions, I want you to let me know if you have anything that's given you trouble or any questions you want to ask about what we've done to get to this point. Outstanding. Okay, let's answer some questions. The first one here says, what is the probability that they're both yellow? Both yellow. So this is probability of yellow followed by yellow. If you were just given this question out of the blue, you wouldn't necessarily need a tree diagram for this because this is a single specific outcome, yellow followed by yellow. You could just do that. You wouldn't have to draw a tree. Since we've drawn the tree, let's go back and see yellow followed by yellow. That's down here. That's 2 out of 56. So that's our probability of yellow followed by yellow is 2 out of 56. Not very good. Very small chance of this happening, which makes sense if you think about the circumstances we're working with. Now we get to the types of problems that do not have a single specific outcome. The probability of getting at least one blue marble. At least one. At least. So that's one or more. Very important to remember what at least means. At least one blue. All right, well, let's go see what we've got here. at least one blue. Well, here has at least one blue, this has at least one blue, and this has at least one blue. This does not. So what that means for me is I can get at least one blue this way, or this way, or this way. So I need to add those probabilities together. So that'll be 30 out of 56 plus 12 out of 56 plus 12 out of 56. We'll add all those together. And let's see, adding the numerators, 30 and 12, that's 54 out of 56. The probability that I get at least one blue is 54 out of 56. Let me know if you have any questions on that one. Before I have you try that one at the bottom there. And the one at the bottom says, what's the probability that the second marble is yellow? And this is the one I'm going to set up a poll for. Probability that the second marble is yellow. I'm going to go back here so you can see that sample space, and I'll make a poll for this one. So what's the probability that the second one is yellow? This is absolutely the type of question you could expect to see on a quiz or an exam. I think it's a challenging question, but I don't think that's a bad thing. I think it's a good thing that, this is the type of question you can expect to see on a quiz or an exam. So I want to make sure that you're comfortable with our process on how to do this one. We'll go another 15 seconds and then we'll talk about it. All right, let's see what we've got here. Not unanimous, but close. All right, that's good news. As we go through it, if you have any questions you want to ask, make sure you do that. All right, so let me get some stuff out of the way here, and then we'll do this one. All right, so what we were asked for in this one was, what is the probability that the second one is yellow? So what we need to do is just find within our sample space the places where the second one is yellow. Well, blue followed by blue. Nope, second one's not yellow. Blue followed by yellow. Sure enough, the second one's yellow there. Yellow followed by blue. No, the second one's blue, so that's no good. Yellow followed by yellow. Yes, the second one's yellow. So I could get the second one yellow this way or this way. So I'll add those together. Add the numerators, 12 and 2 is 14. Add the keep the denominators the same, 56. And so the probability that the second one is yellow is 14 out of 56. The way you would go about answering that question from the beginning, because you might just get this right here. Oops, excuse me. A jar contains 6 blue and 2 yellow. 2 marbles will be drawn, one after the other without replacement. Find the probability that the second marble is yellow. So your thought process is, okay, that's not a single specific outcome. It's possible there's more than one way to do this, so I'll need to make a tree diagram. We build the tree diagram. We use that tree diagram to create a sample space that has all of our probabilities in it. Then we go identify the successes. And if there's more than one way to have a success, we add those probabilities together. So that's our process, kind of start to finish, based on the type of problem you might see. Are there any questions on what we did there to get that? Before I kind of give you a chance to do a tree diagram question from start to finish. All right, fantastic. I trust you. Here goes. An ice chest contains 9 cans of ginger ale and 5 cans of orange soda. 2 cans will be drawn one after the other without replacement. Find the probability of getting exactly 1 orange soda. So your thought process here is exactly 1, not a single specific outcome. Going to have to make a tree diagram. I'm going to let you make the tree diagram here, use it to get the sample space, and then answer this question. I'll set up a poll for it, and I'll give you some time to work on this one. And this is exactly the type of question that I want to make sure you're able to do. Just a reminder of your process here. You're going to make your tree diagram, put the probabilities on it each step of the way, and then use that tree diagram and those probabilities to create your sample space. And then once you have your sample space, you can answer whatever question gets thrown your way. This question happens to be, what's the probability of exactly 1 orange? So we need to identify those successes in our sample space. And then once we identify those successes in the sample space, if there's more than one way to have a success, we'll need to add those together. But what you're seeing on the screen right now, that's what a question would look like on a quiz or an exam. And if you're able to solve it, then that's fantastic. And you're in really good shape, because this is as challenging as these tree diagram questions get. If you have trouble solving this, the best thing we can do is iron that out while we're in class together, before I, turn you loose later to go work on problems from the book and the worksheet. It can take a little time to draw a tree diagram and put the probabilities on and then find the sample space. So these are questions you don't want to be in a hurry when you're working on them. Be patient, be careful. One little mistake in putting a probability on any one of those paths and it can derail the whole thing. So you want to make sure you're patient and careful. The more of them you do, the easier it gets. The more practice you give yourself, the better you will be at these. They can be fairly challenging, so I want to make sure that you get whatever questions you have answered and that you give yourself sufficient time to practice. Let's go another 30 seconds and then we'll talk about it together. If you need more time, it's perfectly fine to just say so. All right, let's see how we did on this one. Unanimous. Well, that's good news. That gives me a lot of confidence. All right, I'll go through this one relatively quickly for us then, since it seems like we're in pretty good shape with what is effectively the top of the mountain for us. So let's take a look here just to make sure we're comfortable. Can't hurt to see it done. There's ginger ale and orange soda in my cooler. So as I build my tree diagram, what I'm going to create then is a path for ginger ale and a path for orange soda. There are 14 total cans, so the probability of getting ginger ale is 9 out of 14. 9 out of 14. The probability of getting orange soda is 5 out of 14. Then I'm going to get another can out, ginger ale, orange soda. And since the first one I got out was a ginger ale, then there's going to be 8 out of 13 for ginger ale. And for orange soda, well, all 5 are still there, so that's 5 out of 13. The second one down here is going to be ginger ale or orange soda. This time, the first one I bought was orange, so all 9 ginger ales are still there, so the probability of ginger ale is 9 out of 13. The probability of orange is going to be 4 out of 13. If you have any questions, make sure you ask them. Now we're going to create our sample space here. We're going to do that by walking along these paths. Ginger ale. And 9 times 8 is 72. 14 times 13 is 182. And so the probability of getting ginger ale followed by ginger ale is 72 out of 182. We'll do this with every one of our possible outcomes. Ginger ale, orange. 9 times 5, that's 45 out of 182. Orange followed by ginger ale, that's going to be 45 out of 182. And then orange followed by orange, going to be 20 out of 182. If any of those numbers don't make sense, you let me know. But since the poll went so well, I feel pretty good about it. Doesn't mean you can't ask questions. Now we've created our sample space. We're done multiplying at this point. We're just going to use that sample space to answer questions. The question I was asked is, what's the probability of getting exactly 1 orange soda? And when I look here, let's see, that's 2 ginger ales. That's ginger ale orange. That's 1 orange soda. Orange ginger ale, that's 1 orange soda. Orange, that has orange in it, but it's 2, and that's no good. I need exactly 1. So I could get exactly 1 orange this way or this way. I'll add those together and have 90 out of 182. If I were asked to write this as a decimal rounded to the nearest 100, I would just divide 90 divided by 182, and rounded to the nearest 100th, I would have 0.49. Let me know if you have any questions on that before I ask you a couple of more questions related to this exact same situation. So we're going to stay with this ginger ale orange soda question for a little bit. We already have our sample space though, so that'll make things much simpler. Here goes. Same exact situation. 9 cans of ginger ale, 5 cans of orange soda, 2 cans drawn one after the other without replacement. This time it's find the probability of at least one ginger ale. So find the probability of at least one ginger ale. I'm going to go back to that other page and set up a poll for this one. So it's really important to be comfortable with the words exactly and at least. This time we want the probability of at least one ginger ale. And it's not on the screen, but you can see it right there in the poll. Probability of at least one ginger ale. If you were given this question from the start, you'd have to draw your tree diagram, put your probabilities on there, multiply along each path to get your sample space, and then use the sample space to answer the question. Here, we already have our sample space, so all we need to do is answer the question. What is the probability of getting at least one ginger ale? You can imagine yourself, you're at the pool and you've got this cooler and you know, get me a soda out of the cooler. Make sure you get me a ginger ale. If you reach in at random and you need at least one to be a ginger ale, what's the probability that that's going to happen? That's what we're after here. And we'll go another 15 seconds and then we'll talk about it. If you need more time, let me know. All right, let's see how we did on this one. Unanimous. That is fantastic. I have to tell you, this is a topic that is consistently fairly challenging. And what I'm seeing so far today is that it's going to go extremely well for you folks. All right. So the question we were asked this time is, what's the probability of at least one ginger ale? So what we'll do, we'll go back and we'll say, all right, well, this has at least one ginger ale, and so does this, and so does this. So I need to add those together. Down at the bottom, that does not have at least one ginger ale, so I don't want to include that. But I need to add those other ones together. And when I add those, 72 out of 182 plus 45 out of 182 plus 45 out of 182, I get 162 out of 182. If we were asked to write that as a decimal, we just divide. You don't have to reduce the fraction. 162 out of 182. All right, one more to go on this situation. What is the probability? I'm very confident in this one. What's the probability the second can is orange? Just like I did for the last one, I'll go back and put the sample space on the screen and then make a poll for the probability that the second can is orange. Let me get rid of some of this first. There we go. And we're after the probability that the second can is orange. Give me just a minute. You'll be done before I make the poll. That's okay. One thing I want you to notice about all three questions we did with this ginger ale orange soda scenario is they all were not a single specific outcome. If a question was drawn like this and said, what is the probability of getting ginger ale followed by orange? You wouldn't have to use a tree diagram. Instead, you could just find the probability of ginger ale, find the probability of orange after it, multiply those together. But when it's a question like we've seen here, exactly one orange, at least one ginger ale, or the second one is orange, that's when we need to use a tree diagram because we're not after a single specific outcome. All right, here we're looking for the probability the second can is orange. Let's go another 15 seconds and then we'll talk about that one. My expectation is this will go well. Unanimous again. All right. I feel really good about where you are on these types of questions. Just to make sure you see it, what we've got here then is we're going to say, okay, I need the probability that the second one is orange. And if the second one needs to be orange, then ginger ale is no good. Ginger ale, orange. Yes, that's a success. Orange, ginger ale. Nope. Second one wasn't orange. Orange. Yes. Second one is orange. I could get second one orange this way or this way. So I add those together and get 65 out of 182. Let me know if you have any questions on that before we put this ginger ale and orange question behind us. Okay. Here's one called Lady and the Tiger. It's an old, I guess fairy tale, where the idea is you're the prince and what you want to do is find the lady. The king says, all right, I'll tell you what. Here's the maze. You're going to walk through this maze. And in one room, there's going to be a lady that you can marry. In another room, there's going to be a tiger that's going to eat you. Where do you want the lady to go? And if you're a smart prince, you don't want to do this at random. You want to think this through a bit and say, all right, well, what is the probability that I'm going to end up in this blue room? What's the probability that I'm going to end up in this green room? And at least I want to give myself the best possible chance. So let's take a look at this. Prince comes walking, and now there are 3 different paths he could take. And, we're not going to try to get inside the prince's head here. There's a 1/3 chance he goes up there, a 1/3 chance he goes straight ahead, and a 1/3 chance he goes to the bottom. All right, well, let's say he walks up this route and now he's here and he has a decision to make. Once he's there and has a decision to make, he could go this way or this way. So this probability is 1/2 and this probability is 1/2. Let me know if you have any questions or any issues about any of these probabilities I'm putting on here. And he could walk down he could go straight ahead and that just takes him right in the blue room. He could go down here and then he has a decision to make. And it's 1/3 that he goes this way, 1/3 that he goes this way, and 1/3 that he goes this way. All right, so a little bit different than our standard tree diagram, but that is kind of what's going on here. And as we follow this through, we want to follow each path. So if he goes up here, that'll be 1/3 times 1/2. To come out of that little spot right there would be 1/3 times 1/2. So the probability it comes out that exit, multiply numerators, 1 times 1, multiply denominators, 3 times 2. That's 1/6 is the probability it comes out that exit, which would put him in the green room. If he takes this path followed by this one, that's 1/3 times 1/2. So it's 1/6 that he comes out of that exit. This one, he just walks straight ahead. There's nothing to multiply. There's just a 1/3 chance that he comes out right there. And then if he goes down, that's going to be 1/3 times 1/3. So 1 times 1 is 1. 3 times 3, that's 1/9 that he comes out that exit. 1/3 times 1/3, it's 1/9 that he comes out that exit. And then 1/3 times 1/3, it's 1/9 that he comes out that exit. Now we've got fractions all over the place. Keeping the main question in mind here is, which room is he going to end up in? What we need to do now is, if we look at the green room, those probabilities are 1/6, 1/9, and 1/9. So he could end up in the green room this way, or this way, or this way. So we need to add those together. The probability he's going to end up in the green room is going to be 1/6 plus 1/9 plus 1/9. As a math teacher, this question's beautiful because now we have to add fractions that don't have a common denominator. So we have to remember back to Math 122 and working with fractions. 9 and 6. What will 9 and 6 both go into? You could certainly use 54. There's nothing wrong with that. But the lowest common denominator here, I could use 18 because 9 and 6 will both go into 18. If I multiply the denominator by 3, I have to multiply the numerator by 3. We've created an equivalent fraction. 3/18 is equivalent to 1/6. They have the same value, but in this problem, writing it as 3/18 is the way that I need to do it because I need my other fractions to have the same denominator. Multiply the denominator by 2, multiply numerator by 2, denominator by 2, numerator by 2. Now they all have a common denominator, so I can add those. Add the numerators, 3, 4, 5, 6, 7 over 18. So the probability he's going to end up in the green room is 7/18. Right there, you might say, well, that's less than half, so he should put the lady in the blue room. Perfect, excellent, you're right. But just for the practice of it, I want to find the probability of ending up in the red room, which is going to be 1/6 plus 1/3 plus 1/9. As it turns out, 18 is going to be our least common denominator there also. We're going to rewrite each of these fractions with 18 as our denominator. Multiply denominator by 3, numerator by 3. Denominator by 6, numerator by 6. We're saying that 6/18 has the same value as 1/3. Denominator by 2, numerator by 2. And now we add these. 3 and 6 is 9, and 2 is 11/18. So the probability that he ends up in the green room is 7 out of 18. The probability he ends up in the blue room is 11 out of 18. So he would want the lady to be in the blue room so that he doesn't get eaten by the tiger. I think it's a super fun question, but I encourage you to let me know if you have any questions at all about anything we did there. Outstanding. The fraction review is really nice. All right, some homework notes before we wrap it up today. For any question related to probability, keep the most important thing in mind. Probability is successes over outcomes. You'll see a lot of questions in this practice that are just a single specific outcome. When that happens, you don't need to use a tree diagram. You can just find the probability of each one and multiply them together. You don't have to use a tree diagram for everything, but some problems will need you to use a tree diagram. The ones that don't have a single specific outcome, at least one, exactly one. The second one is a certain color. Those kind of things, you want to make sure you use a tree diagram. Be patient and careful as you make it. And then, as always, make sure you answer the questions being asked. That's a little bit about the difference between exactly and at least, because it's important to have that distinction.